I am so glad you have joined me in the hush of the evening. You have found your way to Science Blanket, your own soft space for a quiet mind. Have you ever seen a beam of sun wash across a room and felt as though you were seeing a long, golden stream of a dream? This evening, we are wrapping ourselves in the story of the swiftest thing in our world, specifically the smooth and steady flow of light. We often see light as something that is simply there, but it is really a soft, endless rush, a shimmering wave moving in a perfect balance between the energy of the sun and the stillness of the room. From the light, warm rays that feel like soft silk on your skin to the long, ancient beams from the stars that bring the weight of the ages, the speed of light is the visible sign of the universe's invisible pulse. As we begin, imagine yourself resting on a ray of soft, white light, feeling as fast and as effortless as a shadow on the grass. You do not need to worry about the math of the vacuum or the names of the old glass mirrors tonight. Just let the slow, humming rhythm of the photons wash over you and tuck you in. Allow this blanket of sunbeams and steady motion to be your guide as you move toward a deep and mindless rest. Now, take a slow, easy breath. Feel your chest rise and fall, as smooth and as sure as a low, glowing wave. Let the heaviness of your day dissolve into the soft, blue shadows of the evening. Release your jaw, let your shoulders slide down, and sink into the softness of your bed. Let's explore the quiet wonders of the speed of light together. In the beginning, before we knew how to measure the universe, before we understood the nature of light itself, there were only questions hanging in the still air of ancient Greece. A philosopher named Empedocles stood beneath the endless sky around 490 years before the Common Era began, and he wondered about something no one had dared to question before. He looked at the sun, at the way its light reached across the impossible distance between the heavens and the earth, and he made a claim that seemed almost too bold to believe. Light, he said, does not arrive instantly. It travels. It moves through space like a runner crossing a field, and though we cannot see its journey, it takes time. Even the light of the sun, he believed, must have a speed, must follow some limit written into the fabric of existence itself. But not everyone agreed. Another philosopher, Aristotle, whose thoughts would shape human understanding for thousands of years to come, looked at the same sunlight and reached a different conclusion. To him, light was immediate, arriving the very instant it was born, requiring no time at all to cross the void. For Aristotle, the idea that light could be slow seemed impossible, almost absurd. And so the question remained open, unanswered, drifting through the centuries like a whisper carried on the wind. Time passed, as it always does, quietly and without pause. Empires rose and fell. Libraries burned and were rebuilt. Knowledge moved across continents, carried by travelers and traders, by scholars who wrote in languages that would one day be forgotten and then remembered again. In the year 1021, in a world far from ancient Greece, a scientist named Alhazen sat in the dim light of his study and thought deeply about the nature of seeing. He rejected the old idea that light shot out from our eyes like invisible fingers reaching out to touch the world. Instead, he understood that light must come to us, that it must travel from the objects we see into our eyes, and in doing so, it must pass through the air, through water, through all the substances that fill the space between things. And in his careful thinking, Alhazen realized something important. Light, he reasoned, must slow down when it moves through thick substances, through glass or water, just as a person moves more slowly when wading through a river than when walking on dry land. This meant that light had a speed, a finite speed, even if no one yet knew how to measure it. Decades later, in another part of the world, a scholar named Abu Rayhan al-Biruni watched the world around him and noticed something curious. When lightning split the sky during a storm, he saw the flash instantly, but the thunder always came later, rolling across the landscape like a wave of sound moving through the air. This simple observation told him something profound. Light and sound were not the same. They did not travel at the same pace. Light arrived first, always first, so fast that it seemed almost instantaneous, while sound lagged behind, slower, taking its time to reach the ear. Through philosophical thinking and careful observation, he understood that the speed of light must be vastly greater than the speed of sound, though he had no way to measure either with precision. The universe, he realized, was full of invisible motion, full of things racing through space at speeds beyond human comprehension. But still, no one could catch light in their hands and measure its journey. No one could time its passage from one place to another. The question remained a mystery, beautiful and frustrating, waiting for someone to find a way to answer it. Centuries continued to roll past, bringing new tools, new ways of looking at the heavens. Telescopes were invented, lenses ground and polished until they could pull distant stars closer, until they could show humanity things never seen before. And in the year 1676, a Danish astronomer named Ole Rømer sat at his telescope night after night, watching the moons of Jupiter swing around that giant planet like dancers circling a fire. One moon in particular, a small world called Io, caught his attention. Io disappeared behind Jupiter regularly, slipping into the planet's shadow in a rhythm that should have been perfectly predictable, perfectly regular, like the ticking of a clock. But Rømer noticed something strange. Sometimes Io emerged from Jupiter's shadow a little earlier than expected, and sometimes a little later. The timing shifted, drifted, changed in a pattern that made no sense unless something else was happening, something invisible. Rømer thought about this puzzle carefully, turning it over in his mind like a smooth stone. And then he understood. The light carrying the image of Io to his eyes had to travel across space, and that distance changed as Earth and Jupiter moved in their orbits around the Sun. When Earth was closer to Jupiter, the light had less distance to travel, and Io appeared to emerge from shadow sooner. When Earth was farther away, the light had more distance to cover, and Io seemed to emerge later. The moon itself was not changing its behavior at all. What was changing was the time it took for light to bring the news of that behavior to Earth. For the first time in human history, someone had measured the speed of light, and Rømer calculated it to be roughly 220,000 kilometers per second. It was not exact, not perfect, but it was real. Light had a speed, and now humanity knew it. The universe had revealed one of its secrets, but the investigation was far from over. In the 1800s, a brilliant mind named James Clerk Maxwell sat with sheets of paper covered in mathematical symbols, equations that described electricity and magnetism in ways no one had described them before. Maxwell was trying to understand how these two forces were connected, how they danced together in the invisible spaces between charged particles and magnetic fields. And as he worked through his equations in 1861, something remarkable emerged from the mathematics itself. His equations predicted that electricity and magnetism could create waves together, waves that would ripple through empty space at a specific speed, a speed determined by the nature of those forces. When Maxwell calculated that speed, he found it to be approximately 310,740 kilometers per second. And then he realized something that must have made his heart race. This was almost exactly the speed that light had been measured to travel. Light, Maxwell understood, was not separate from electricity and magnetism. Light was an electromagnetic wave, a rippling disturbance in the electromagnetic field, and its speed was written into the fundamental equations governing those forces. He had unified light with electricity and magnetism, showing they were all part of the same phenomenon, all connected by this one unchanging speed. But scientists are never satisfied with theory alone. They need to test, to measure, to see for themselves. In 1850, a French physicist named Léon Foucault built an ingenious device, a spinning mirror that could reflect light back and forth, allowing him to measure how long light took to travel a known distance. His mirror rotated so fast that by the time light bounced back to it, the mirror had turned slightly, and the reflected light hit a different spot. By measuring that tiny shift, Foucault could calculate the speed of light with new precision. He found it to be 298,000 kilometers per second when traveling through air. But he did something else that was equally important. He measured the speed of light through water and found that it was slower there, just as Alhazen had reasoned centuries before. Light slowed down when passing through thick substances, proving that its speed was not the same everywhere, that the material through which it traveled mattered. The measurements grew more and more precise as the years went by and technology improved. In 1926, an American physicist named Albert Michelson, who had devoted much of his life to measuring light, climbed to the top of Mount Wilson in California. There, high above the world, where the air was thin and clear, he set up an elaborate system of mirrors and lenses, using a technique called interferometry that could detect the tiniest variations in light's journey. His measurement was astonishingly accurate for its time, finding the speed of light to be 299,796 kilometers per second. Each new measurement brought humanity closer to the true value, peeling away layers of uncertainty like removing veils from a hidden face. Then, in 1947, 3 scientists named Essen, Gordon Smith, and another colleague tried something different. Instead of using visible light, they used microwaves, invisible waves of electromagnetic energy that could be controlled with great precision inside specially designed cavities that resonated at exact frequencies. By measuring how these microwaves behaved, they calculated the speed of light to be 299,792 kilometers per second, with an uncertainty of only 9 kilometers per second either way. This was more accurate than any optical method had achieved, and it showed that the speed was the same for all electromagnetic waves, whether they were visible to the human eye or not. By 1972, scientists had developed lasers, devices that could produce light so pure and so precisely controlled that measurements became almost unimaginably accurate. A team led by a researcher named Evanson used laser interferometry to measure the speed of light with an uncertainty of less than 1 meter per second. Think about that for a moment. They knew the speed to within 1 meter per second out of nearly 300 million meters per second. It was like measuring the distance across an entire continent and being accurate to within the width of a single step. And then something remarkable happened. The measurements had become so good, so reliable, that scientists realized they were now more certain about the speed of light than they were about the definition of the meter itself. And so, in 1983, they made a decision that changed everything. They stopped trying to measure the speed of light. Instead, they fixed it, defined it to be exactly 299,792,458 meters per second, not because they measured it to be that, but because they decided it was that. and then they redefined the meter itself based on this fixed speed. Now, 1 meter is the distance that light travels in a vacuum during exactly 1,299,792,458th of a second. Light itself had become the ruler by which we measure all distance, the clock by which we mark the passage of space itself. From the ancient philosophers wondering if light could be caught and measured, through centuries of increasingly precise experiments, humanity had finally pinned down the speed of light with such accuracy that it became the foundation of measurement itself. But understanding how fast light travels was only the beginning of a much deeper mystery. The speed of light, it turns out, is not just a number, not just a fact to be memorized and repeated. It is woven into the very structure of reality, into the way space and time fit together, into the rules that govern everything that exists. And discovering this required someone to think about motion and light in a way no one had ever thought before. In the early 1900s, a young man working in a patent office in Switzerland spent his spare time thinking about what it would be like to ride alongside a beam of light. His name was Albert Einstein, and the questions he asked himself seemed simple at first but led to conclusions that would shake the foundations of physics. He wondered what would happen if you could travel at the speed of light and look at a light wave beside you. Would it appear frozen, motionless, like a wave on the ocean caught in a photograph? The more he thought about this, the more he realized that something was deeply wrong with the way people understood motion. And from this thinking emerged a principle so strange and so fundamental that it changed everything. The speed of light, Einstein realized, must be the same for everyone, no matter how fast they are moving. If you are standing still and measure the speed of a passing light beam, you will find it travels at exactly 299,792,458 meters per second. And if you are racing through space at half that speed and measure the same light beam, you will still find it travels at exactly the same speed relative to you. This seems impossible, like a contradiction, like something that cannot be true. But experiment after experiment, starting with one called the Kennedy-Thorndike experiment and continuing through countless others over more than a century, has confirmed this strange fact again and again. The speed of light is invariant, unchanging, the same in all inertial frames of reference, which is a fancy way of saying it is the same for everyone who is not accelerating. This is one of the core postulates of special relativity, the theory Einstein published in 1905, and it means that the universe behaves in ways that defy our everyday intuition. This invariance of light speed leads to conclusions that seem like they belong in dreams rather than in reality. If light always travels at the same speed no matter how fast you are moving, then something else must change to make that possible. And what changes, Einstein showed, are space and time themselves. They are not fixed, not absolute, not the same for everyone. They bend and stretch and shift depending on how fast you are moving. One of the most profound consequences of this is that nothing with mass can ever reach the speed of light. As an object with mass moves faster and faster, approaching the speed of light, something happens to it. There is a mathematical factor, called the Lorentz factor, represented by the Greek letter gamma, and it appears in equation after equation describing how things behave at high speeds. This factor equals 1 divided by the square root of 1 minus the speed of the object squared divided by the speed of light squared. When something is moving slowly compared to light, this factor is very close to 1, and everything behaves normally. But as the speed increases, as it gets closer and closer to the speed of light, this factor grows larger and larger. And as the speed approaches the speed of light exactly, the Lorentz factor approaches infinity. What this means is that to accelerate an object with mass all the way up to the speed of light would require infinite energy, an impossible amount, more energy than exists in the entire universe. The speed of light is not just a speed limit in the sense of a rule posted on a highway. It is a fundamental barrier built into the structure of space-time itself, unreachable by anything that has mass. But there are things in the universe that have no mass at all, particles so insubstantial that they are nothing but pure energy rippling through space. Photons, the particles of light itself, have no rest mass. Neither do gluons, the particles that hold the nuclei of atoms together by carrying the strong nuclear force. And gravitons, if they exist as particles of gravity, would also have no mass. All of these massless particles travel at exactly the speed of light in vacuum, never faster, never slower. They are born moving at this speed and can never do anything else. They experience no time, no passage of moments from their own perspective. From the point of view of a photon, if a photon could have a point of view, the instant it is created and the instant it is absorbed are the same moment, with no time in between, even if that journey takes billions of years from our perspective as the photon crosses the universe. The speed of light appears in other equations too, equations that reveal deep truths about the nature of existence. Perhaps the most famous equation in all of physics is E = mc squared, three simple symbols that carry within them an explanation for the power of the sun, the devastation of nuclear weapons, and the fundamental equivalence of mass and energy. The c in this equation is the speed of light, and it is squared, multiplied by itself, producing an enormous number. What this equation tells us is that mass and energy are not separate things but different forms of the same thing. Mass is concentrated energy, frozen energy, energy that has taken on a tangible form. And because the speed of light is so large, even a tiny amount of mass corresponds to an immense amount of energy. A single kilogram of matter, if it could be completely converted to energy, would release 90 million trillion joules, enough to power a large city for months. This is why stars shine, why they can burn for billions of years without running out of fuel. In their cores, hydrogen atoms are squeezed together under such intense pressure and heat that they fuse into helium, and in that process, a tiny fraction of their mass is converted into energy according to Einstein's equation. That energy streams outward as light and heat, warming planets across billions of kilometers of empty space. But the consequences of the speed of light being finite and invariant do not stop there. Time itself behaves differently depending on how fast you are moving. There is a phenomenon called time dilation, and it means that time passes more slowly for objects that are moving quickly relative to objects that are moving slowly or standing still. The equation that describes this uses that same Lorentz factor, and it tells us that the time experienced by a moving object is equal to the time experienced by a stationary observer divided by the square root of 1 minus the velocity squared divided by the speed of light squared. This sounds abstract, like pure theory disconnected from everyday life, but it is absolutely real and has been proven again and again. High-energy particles called cosmic rays stream into Earth's atmosphere from deep space, traveling at speeds very close to the speed of light. Some of these particles are muons, unstable particles that decay into other particles in just a few millionths of a second. At the speed they travel, they should decay long before they reach the ground. But they do not. They survive the journey and are detected at the surface because, from our perspective, time is passing more slowly for them. Their internal clocks are running slow, stretched out by their incredible speed, giving them more time to complete their journey. This same effect is built into the GPS satellites that orbit Earth and tell us where we are when we navigate with our phones. Those satellites are moving quickly relative to the ground, and they are also farther from Earth's gravity, which affects time in its own way. Engineers must account for time dilation in both directions, correcting for the fact that time passes at a different rate for the satellites than it does for us on the surface. Without these corrections, GPS would drift out of accuracy by kilometers in just a single day. And there is another effect, equally strange, called length contraction. Objects that are moving very fast do not just experience time differently, they are also physically shorter in the direction they are moving. The amount of contraction is given by multiplying the original length by the square root of 1 minus velocity squared divided by the speed of light squared. This means that a spaceship traveling at 90% of the speed of light would appear, to a stationary observer, to be compressed to less than half its original length along its direction of motion, though the passengers inside would notice nothing strange at all. From their perspective, they are not contracted. Instead, it is the universe outside that appears compressed, distances shortened, making the journey to distant stars seem shorter than it would to someone watching from Earth. Scientists have tested the invariance of the speed of light over and over, using increasingly sensitive instruments, looking for any sign that it might vary even slightly under different conditions or at different times or in different directions. Experiments using laser spectroscopy have been able to set limits on any possible variation in the speed of light to less than 1 part in 10 to the 21st power per second, a level of precision almost impossible to comprehend. These are called Lorentz invariance tests, and they confirm again and again that the speed of light is exactly the same in all directions, at all times, under all conditions, as far as we can measure. The speed of light does not just set a limit on how fast things can move. It actually defines the geometry of space-time itself, the four-dimensional fabric in which all events occur. There are mathematical transformations called Lorentz transformations that describe how measurements of space and time made in one frame of reference relate to measurements made in another frame moving at a different speed. These transformations have the speed of light built into them, and they show how space and time mix together, how what one observer measures as a distance in space, another observer moving differently might measure partly as a distance in time. The metric of space-time, the equation that tells us how to measure distances and durations in this four-dimensional universe, includes the speed of light as a fundamental constant. It appears as a negative term multiplied by time squared, showing how time is different from the three dimensions of space, related but distinct, all bound together by this one unchanging speed. It is interesting, in a quiet way, to think about where the symbol for the speed of light comes from. We write it as the letter C, a simple character that now represents one of the most important constants in all of physics. Most scientists believe the letter was chosen because of the Latin word celeritas, which means swiftness or speed. A German physicist named Max Abraham seems to have been the first to use C specifically for the speed of light in print, in a paper from 1903, though others may have used it in their notes before that. Before C became standard, different scientists used different symbols, sometimes V for velocity or other letters. But C caught on, and now it is universal, understood by physicists in every country, in every language, a single letter carrying the weight of all these deep truths about reality. In some branches of physics, especially when working with relativity, scientists use what are called natural units, a system of measurement where the speed of light is simply set equal to 1. This might seem strange at first, but it makes the mathematics much simpler and reveals relationships between quantities more clearly. In natural units, Saying something travels at the speed of light means it travels 1 light second per second, which is just 1. Energy and mass have the same units because they are related by c², which is now also just 1. Time and distance have the same units because they are connected by the speed of light. This is not just a mathematical trick. It reflects a deep truth about the universe, that space and time are not fundamentally separate things but aspects of a single unified structure, and the speed of light is the conversion factor between them, the thread that stitches them together into space-time. When we talk about the speed of light as a number, as nearly 300 million meters per second, it can be hard to grasp what that really means, hard to feel it in a way that connects to our everyday experience of moving through the world. We are used to speeds we can relate to, the pace of walking, the rush of a car on a highway, the roar of an airplane cutting through the sky. But light moves so much faster than any of these that it exists in a different realm entirely, almost beyond imagination. And yet, there are ways to bring it down to earth, to understand it through comparisons and examples that make the impossible seem just a little more real. Imagine the Earth beneath your feet, this sphere of rock and water and air spinning slowly through the darkness of space. The equator wraps around the planet like a belt, stretching for just over 40,000 kilometers, a distance it would take months to walk. But light, traveling at its constant speed, circles the entire Earth 7.5 times in a single second. In the time it takes you to blink, light has raced around the planet multiple times, over and over, never slowing, never resting. It is a speed so great that distance on Earth almost ceases to have meaning for it. The farthest points on the planet are connected by light in a fraction of a heartbeat. And if we look up, beyond the atmosphere, beyond the edge of space where the sky fades to black, we find the moon hanging in the void, that pale companion that has watched over Earth for billions of years. The moon sits, on average, about 384,000 kilometers away, a distance that took the Apollo astronauts 3 days to cross in their spacecraft. But light makes the journey in 1.26 seconds. When you look up at the moon on a clear night, you are not seeing it as it is in that exact moment. You are seeing it as it was just over a second ago, looking back through time because light takes time to travel, even across that relatively short gap. Every image we see, every photon that enters our eyes, carries with it a message from the past, near or distant depending on how far it has traveled. If we express the speed of light in more familiar units, in kilometers per hour the way we measure the speed of a car, the number becomes 1,080,000,000 kilometers per hour. It is a number so large it almost loses meaning, but think of it this way. The Sun sits at the center of our solar system, a burning sphere of hydrogen and helium so massive that more than 1,000,000 Earths could fit inside it. The distance from the Sun to Earth averages about 150 million kilometers, a void so vast that no human has ever traveled even a tiny fraction of it. Yet light crosses this distance in 8.3 minutes. When you step outside and feel the warmth of sunlight on your skin, that warmth left the surface of the Sun more than 8 minutes earlier. The Sun could vanish, could blink out of existence, and we would not know it for 8 minutes. We would continue to see it shining in the sky, continue to feel its heat, living in a world that had already changed, unaware that the source of all our light and life had disappeared. Astronomers measure the distances between stars not in kilometers or miles, because those numbers become unwieldy, too many zeros to write or comprehend. Instead, they use a unit called the light year, the distance that light travels in one full year. Not a calendar year with its irregular months and leap days, but a Julian year, exactly 365 1/4 days, which equals 31,557,600 seconds. Multiply that by the speed of light and you get 9,460,000,000,000 kilometers, a distance so enormous that the human mind cannot truly grasp it. This is our basic yardstick for measuring the cosmos. The nearest star beyond the Sun, a small red dwarf called Proxima Centauri, lies 4.24 light-years away. The light we see from it tonight left that star more than 4 years ago, before the last presidential election, before the pandemic reshaped the world. We see the past when we look at the stars, not because of some trick or illusion, but because light has a speed and distance takes time to cross. To put it another way, in the single second it takes to say the word Mississippi, light travels far enough to circle Earth at the equator 7.48 times, wrapping around and around, crossing oceans and continents, deserts and forests, cities sleeping and cities waking, all in the span of 1 second. And if we think smaller, more locally, consider the width of the United States, from the Atlantic coast to the Pacific, roughly 4,500 kilometers depending on where you measure. Light crosses that entire distance in 13.5 milliseconds, 13.5 thousandths of a second, faster than the blink of an eye, faster than the beat of a hummingbird's wing. There is a spacecraft called Voyager 1, launched in 1977, now drifting through interstellar space beyond the edge of the solar system, farther from home than any object humans have ever created. It is more than 24 billion kilometers away, and it continues to send signals back to Earth, faint whispers of radio waves carrying data about the void through which it travels. Those signals move at the speed of light, the fastest speed at which information can travel, and they take 22.5 hours to reach us. When engineers send a command to Voyager, they must wait 45 hours for a response, 22.5 hours for the command to arrive, and another 22.5 hours for the confirmation to return. It is a conversation conducted across an almost unimaginable distance, each exchange taking nearly 2 days, a reminder of how vast even our own solar system is, how much emptiness lies between the worlds. The speed of light is so fast compared to anything in our daily experience that it can make the universe seem small, distances trivial. But there is another speed we should consider for comparison, the speed at which signals travel through our own bodies. Human nerve impulses, the electrical signals that carry sensations from your fingertips to your brain, or commands from your brain to your muscles, travel at a maximum speed of about 100 meters per second. This sounds fast, and compared to walking it is fast, but compared to light it is glacially slow. A nerve signal takes several milliseconds to travel from your toe to your brain, which is why there is a tiny delay between stubbing your toe and feeling the pain. Light, crossing the same distance through the air, would take only a few nanoseconds, a few billionths of a second. Our biology operates on a timescale measured in thousandths of a second, while light operates on a timescale measured in billionths. We live in a slow world compared to the speed at which the universe can transmit information. This slowness of biological signals actually matters in ways that might not be obvious at first. For life to exist, for any living creature to function, signals must be able to travel through the body fast enough that the organism can react to its environment before something important changes. A mouse needs to process the sight of a hawk and run before the hawk strikes. A tree needs to move water from its roots to its leaves before it dries out, though trees can afford to be slower because their threats are slower too. There is a relationship between how large a creature is and how long it lives, and part of that relationship comes down to the speed of signals. Larger creatures have farther for signals to travel, and if those signals move at the speed of nerve impulses, there is a limit to how large and how fast a creature can be and still function. Life requires that the ratio of age to size allows signals traveling slower than light to process information and coordinate action before death or disaster occurs. A whale can be enormous because it moves slowly and lives in an environment where threats are also slow. But a creature the size of a whale that needed to react as quickly as a hummingbird would face impossible challenges coordinating its body. If humans ever hope to travel to the stars, we must confront the reality that we are fragile creatures adapted to gentle accelerations and moderate speeds. To accelerate a human being to the speed of light, even if it were physically possible, would require overcoming not just the infinite energy problem but also the crushing force of acceleration itself. If you accelerated at 3 times Earth's gravity, 3gs, a force that fighter pilots sometimes experience and can endure for short periods, it would take nearly a year of constant acceleration to reach the speed of light if the laws of physics allowed it, which they do not. But even at accelerations we can survive. The long-term effects of sustained g-forces are unknown, potentially causing damage to the brain, the heart, the circulatory system. We are built for the gentle 1g pull of Earth, and extended exposure to higher forces might break us in ways we do not yet understand. And there is another problem, one that emerges when we think about what it would mean to travel through space at speeds anywhere close to the speed of light. Space is not empty. There are atoms out there, hydrogen mostly, spread thin across the void, only a few atoms per cubic centimeter on average, but they are there. At low speeds, these atoms are harmless, drifting past like dust motes in a sunbeam. But at high speeds, they become weapons. An atom striking a spacecraft at a significant fraction of the speed of light carries enormous kinetic energy, energy proportional to velocity squared. At speeds of even 15 kilometers per second, modest compared to light's 300,000 kilometers per second, impacts begin to cause damage. At speeds approaching a significant fraction of light speed, every atom becomes a bullet, and a spacecraft moving through space would be sandblasted by collisions that could tear apart molecules, shred the hull, destroy anything in their path. This is one of the many reasons why cosmic life, if it exists elsewhere in the universe and travels between stars, must stay far below the speed of light, crawling slowly through the cosmos to avoid being destroyed by the very medium through which it travels. The speed of light is the ultimate speed limit, but for any creature made of matter, for any ship built of atoms, the practical limit is far lower, dictated not by the geometry of spacetime but by the simple brutal physics of collision and momentum. The speed of light in vacuum is absolute, unchanging, a fundamental constant woven into the fabric of spacetime itself. But the universe is not made only of vacuum. It is filled with matter, with substances both familiar and strange, with air and water and glass and diamond, with gases and liquids and solids, each one a different arrangement of atoms and molecules. And when light passes through these materials, something interesting happens. It slows down. Not because the photons themselves are moving more slowly, but because of the way they interact with the matter around them. Light entering a substance is absorbed by atoms and then re-emitted over and over countless times, in a process so rapid it appears continuous. This interaction takes time, and the effect is that light appears to travel more slowly through the material than it does through empty space. The degree to which light slows depends on the substance, on how densely packed its atoms are, on the structure of its molecules, on properties that scientists capture in a number called the refractive index. Water, clear and familiar, the substance that covers most of our planet and fills our bodies, has a refractive index of about 1.33. This means that light travels through water at about 1 divided by 1.33 times the speed it travels in vacuum, which works out to roughly 225,000 kilometers per second. Still incredibly fast, still far beyond anything we experience in daily life, but noticeably slower than light's maximum speed. This is why things look different underwater, why a stick appears bent when you dip it into a pond, why the bottom of a swimming pool seems closer than it really is. Light bends as it moves from air into water because of this change in speed, refracting at the boundary between the two substances. Diamond, that crystalline form of carbon prized for its brilliance and hardness, slows light even more dramatically. With a refractive index of about 2.42, diamond reduces light's speed to roughly 124,000 kilometers per second, or if you prefer older units, about 77,500 miles per second. The dense lattice of carbon atoms, each one bonded tightly to its neighbors in a rigid geometric structure, interacts strongly with passing photons, causing this significant slowdown. This is part of what gives diamond its famous sparkle. Light entering a diamond slows and bends sharply, reflects off the internal facets, and emerges at angles that send flashes of color in all directions, turning white light into a spectrum of brilliance. But the story of light and speed in materials is more subtle and strange than simply saying light slows down. There are different kinds of speed we can talk about when discussing waves, and they do not all behave the same way. There is something called phase velocity, which describes how fast the peaks and troughs of a wave pattern move through space. In certain special structures called waveguides, carefully designed channels that constrain how waves can move, the phase velocity can actually exceed the speed of light in vacuum. This sounds like it violates everything we have discussed about light speed being a universal limit, but it does not, because phase velocity is not the speed at which information travels. You cannot send a message, cannot transmit energy or information, using phase velocity alone. The peaks of waves rushing along faster than light carry no meaning, no signal. They are like shadows racing along a wall, able to move faster than the object casting them without violating any physical law because the shadow itself is not a thing, just an absence of light. There is another kind of speed called group velocity, which describes how fast a pulse or packet of waves travels, a collection of different frequencies moving together. In certain materials with special properties called anomalous dispersion, where different frequencies of light travel at different speeds in unexpected ways, the group velocity can also exceed the speed of light in vacuum. But once again, no information actually travels faster than light. There is yet another speed called the front velocity, the speed at which the very first disturbance, the leading edge of a signal, propagates through space, and this front velocity never exceeds the speed of light. It cannot. The universe does not allow it. These superluminal phase and group velocities, faster than light velocities that appear in certain materials and circumstances, are real measurements but do not violate causality or allow for faster than light communication. They are subtle effects that remind us how complicated waves can be, how the mathematics of wave propagation contain surprises and apparent paradoxes that disappear when examined carefully. In some types of glass designed for X-ray wavelengths, the phase velocity exceeds the speed of light in vacuum, racing through the material faster than light would travel through empty space. This seems impossible, and yet it happens, and it is harmless because, as we have said, phase velocity carries no information. You cannot use this effect to send a message faster than light. The information in any signal, the part that matters, the part that could be used to communicate, still travels at or below the speed of light in vacuum. The universe preserves its own consistency, maintains its own rules, even when it seems to bend them. At the other extreme, scientists have found ways to slow light to speeds that seem almost absurd, almost motionless. In incredibly cold clouds of atoms called Bose-Einstein condensates, where temperatures drop to just fractions of a degree above absolute zero and atoms lose their individual identities and merge into a single quantum state, light can be slowed to about 60 kilometers per second. This is slower than the speed at which the Earth orbits the Sun, slower than the escape velocity from Earth's gravity. The light is not truly changing its fundamental speed. Rather, the photons are being absorbed and re-emitted by the atoms in the condensate over and over in a carefully orchestrated way that makes the overall progress of a light pulse through the material incredibly slow. It is a quantum trick, a manipulation of how light and matter interact, but the effect is real and measurable. Even more dramatically, there are certain films made from bacterial proteins that can slow light to less than 1/10 of a millimeter per second at room temperature, no extreme cold required. This is done through a process called coherent population oscillation, where the quantum states of the molecules in the film are manipulated so that they interact with light in a very particular way. Light entering such a material creeps through it slower than a snail crawls, slower than a clock's second hand moves. These are laboratory curiosities at present, demonstrations of how deeply we can manipulate the behavior of light when we understand the quantum mechanical interactions between photons and atoms. They hint at possibilities for controlling light in ways that might one day be useful for storing information, for building new kinds of computers, for technologies we have not yet imagined. There is a beautiful phenomenon that occurs when charged particles move through a transparent medium faster than light travels in that medium. Remember, light slows down in materials, so even though nothing can exceed the speed of light in vacuum, particles can exceed the reduced speed of light in a substance. When they do, they emit a kind of optical shock wave, a cone of light spreading out behind them, similar in principle to the sonic boom created by an aircraft exceeding the speed of sound in air. This light is called Cherenkov radiation, named after the Russian physicist who studied it, and it has a distinctive blue glow. It is the reason that pools of water surrounding nuclear reactors glow with that eerie blue light, the light emitted by particles racing through the water faster than light itself can travel through it. The effect is not just beautiful, it is useful. Scientists use Cherenkov radiation detectors to study high-energy particles from space, to understand neutrinos and cosmic rays, to probe the fundamental nature of matter. The same slowing of light in materials that creates Cherenkov radiation also makes possible one of the most important technologies of the modern world, fiber optics. These thin strands of glass, thinner than a human hair, carry light signals across continents and under oceans, forming the physical backbone of the Internet, the infrastructure through which digital information flows. Light traveling through optical fiber moves at about 200,000 kilometers per second, slowed by the glass's refractive index of approximately 1.5. This is about 2/3 the speed of light in vacuum, which means signals traveling around the world still take a noticeable fraction of a second. When you send a message to someone on the other side of the planet, there is a delay, a lag caused by the finite speed at which information can travel. Light must cross thousands of kilometers of fiber, bouncing down the core of the cable through total internal reflection, losing a little bit of intensity but maintaining its signal until it reaches its destination. Even at 200,000 kilometers per second, distance still matters, and the speed of light becomes a factor in the design of global networks, in the synchronization of financial markets, in the coordination of systems that span the Earth. And light carries information not just through glass fibers but through the air itself. There is a technology called LiFi, which uses LED lights to transmit data by modulating their brightness faster than the human eye can perceive, turning the lights in a room into wireless communication devices. By flickering on and off millions or billions of times per second in carefully controlled patterns, these LEDs can transmit data at speeds exceeding 100 gigabits per second, 100 times faster than typical Wi-Fi. This works because visible light has a much higher frequency than radio waves, a broader bandwidth, more room to encode information. Every light bulb could become a data transmitter, every lamp a connection point in a network that fills the space with information, invisible to us but they're nonetheless riding on the same photons that illuminate our world. The speed of light is not just a curiosity, not just an abstract number that physicists write in textbooks. It shapes our technology, our ability to navigate the world, our understanding of the cosmos. Every time you use your phone to find your location, every time you follow directions to an unfamiliar place, you are relying on a network of satellites orbiting high above Earth's atmosphere. Satellites that must account for the speed of light and the strange effects of relativity to function properly. These GPS satellites carry atomic clocks, incredibly precise timekeepers that measure the passage of seconds with extraordinary accuracy. But these clocks do not tick at quite the same rate as identical clocks on the ground. The satellites are moving at high speed in their orbits, thousands of kilometers per hour relative to the Earth's surface, and this motion causes time dilation. Time passes slightly more slowly for the satellites than for us on the ground. At the same time, the satellites are farther from Earth's mass, experiencing weaker gravity, and general relativity tells us that time passes slightly faster in weaker gravitational fields. These two effects work in opposite directions, but they do not cancel perfectly. When you add them up, the clocks on GPS satellites advance by about 38 microseconds every day compared to clocks on Earth. 38 millionths of a second might seem trivial, but light travels about 300 meters in a single microsecond, and GPS accuracy depends on measuring the time it takes for signals traveling at the speed of light to reach your phone from multiple satellites. Without corrections for relativity, without accounting for these effects that arise from the finite and invariant speed of light, GPS would drift out of accuracy by about 10 kilometers per day, rendering it useless. The convenience of modern navigation exists because engineers understand how the speed of light and the geometry of space-time work together. Deep underground, in tunnels carved through the bedrock beneath the border between France and Switzerland, there is a machine that pushes matter closer to the speed of light than anything else humans have ever built. The Large Hadron Collider is a ring 27 kilometers in circumference, filled with powerful magnets and bathed in extreme cold, and inside this ring, protons race around the circle thousands of times per second, accelerated by electric fields to speed so close to the speed of light that the difference is almost meaningless. These protons reach velocities of 0.999999991 times the speed of light, 11 nines before the one drops off, so close to the ultimate speed limit that they are essentially traveling as fast as anything with mass can travel. And as they approach this speed, the relativistic effects become enormous. Each proton, which at rest has a mass of about 1.67 times 10 to the negative 27 kilograms, gains effective mass as it accelerates, becoming 6,500 times heavier from the perspective of the laboratory. This is not because more matter has been added to the proton. It is because energy and mass are equivalent, linked by that famous equation, and the kinetic energy of motion contributes to the proton's total mass energy. When these protons collide with each other, the energy released is so great that it can create new particles, exotic forms of matter that exist for only fractions of a second before decaying into other particles, allowing physicists to study the fundamental building blocks of reality. The same understanding of light that allows us to navigate with GPS also allows us to transmit information at incredible speeds through tiny channels of glass. Intel and other companies have developed photonic chips, devices that use light instead of electricity to carry signals between components. These chips can transmit data at rates of 1 terabit per second over fiber optic cables, using a technique called wavelength division multiplexing, where multiple different colors of light carry separate streams of data simultaneously down the same fiber. Each color is a different channel, and by using many colors at once, the total capacity becomes enormous. This is how modern telecommunications work, how vast amounts of data flow through undersea cables connecting continents, how the internet sustains billions of users all accessing information at the same time. And the capacity continues to grow. In laboratory experiments, researchers have achieved transmission rates of 1.5 petabits per second over a distance of 25 kilometers, sending data through a fiber that supports 55 different spatial modes, each one modulated at 28 terabits per second. A petabit is 1,000 trillion bits, an almost incomprehensible amount of information. At this rate, you could transmit the entire contents of the Library of Congress in a fraction of a second. These are not yet practical systems deployed in everyday networks, but they show what is possible, how much information can be encoded in light, how the speed and bandwidth of light make it the ideal carrier for the data-hungry world we have created. Light does not just carry human-made signals. It also carries messages from the universe itself, messages that tell us about events so powerful they shake the fabric of space-time. There are objects in space called pulsars, the remnants of massive stars that have collapsed into spheres of neutrons just a few kilometers across but containing more mass than the Sun. These neutron stars spin rapidly, sometimes hundreds of times per second, and they emit beams of radio waves from their magnetic poles. As they spin, these beams sweep across space like lighthouse beams, and if Earth happens to lie in the path of the beam, we detect regular pulses of radio waves arriving with extraordinary precision. By monitoring these pulses from many pulsars spread across the sky, astronomers have created what are called pulsar timing arrays, networks of observations that can detect tiny irregularities in the arrival times of the pulses. When a gravitational wave passes through space, it stretches and compresses distances, causing the pulses to arrive slightly earlier or later than expected. These gravitational waves, ripples in spacetime itself, travel at the speed of light, and by observing the correlated delays in pulsar signals, scientists can detect waves with frequencies of nanohertz, oscillations so slow that they take years to complete a single cycle. The fact that these waves propagate at the speed of light, consistent with what general relativity predicts, confirms our understanding of gravity as a phenomenon involving the curvature of space-time. More direct detections of gravitational waves have come from observatories like LIGO, which use laser interferometry to measure changes in distance smaller than the width of a proton. When two black holes or two neutron stars spiral together and merge, they emit gravitational waves so powerful that even across billions of light-years, they can be detected on Earth. These waves propagate at the speed of light, and measurements show that their speed matches the speed of light in vacuum to within 1 part in 10 to the 15th power, an almost perfect agreement. This is not just a confirmation that gravitational waves travel at light speed. It is a confirmation of general relativity itself, of Einstein's century-old insight that gravity is not a force in the traditional sense but a curvature of spacetime, and that disturbances in this curvature propagate at the same speed as light because they are both aspects of the same underlying geometry. Gravity also bends light, and nowhere is this more dramatic than near black holes. Using an Earth-sized array of radio telescopes working together as a single instrument, the Event Horizon Telescope has captured images of the shadows of supermassive black holes at the centers of distant galaxies. These shadows appear where light that would have escaped is instead bent so strongly by the black hole's gravity that it falls inward, crossing the event horizon and disappearing forever. Just outside the event horizon, at a distance of 1.5 times the Schwarzschild radius, there is a region called the photon sphere, where light can orbit the black hole, trapped in circular paths, neither escaping nor falling in. The images captured by the Event Horizon Telescope show a dark center surrounded by a bright ring of light, photons that have been bent around the black hole before reaching us, visual proof of how extreme gravity warps space-time and alters the paths that light follows. Far from black holes, out in the ordinary space between galaxies, astronomers use exploding stars called Type Ia supernovae as standard candles, objects whose intrinsic brightness is known, allowing distances to be calculated by measuring how dim they appear from Earth. These measurements depend on assuming that the speed of light is constant across cosmic distances and cosmic time. By observing many of these supernovae at different distances and therefore different times in the past, astronomers have discovered that the expansion of the universe is accelerating, driven by some mysterious dark energy that permeates space. This discovery, one of the most important in cosmology, relies fundamentally on the constancy of the speed of light, on our confidence that light we see from distant supernovae travel to us at the same speed as light from nearby stars. In 1987, a supernova exploded in a nearby satellite galaxy called the Large Magellanic Cloud, close enough that it could be studied in unprecedented detail. Before the light from the explosion reached Earth, a burst of neutrinos arrived, tiny particles with almost no mass that interact so weakly with matter that they can pass through entire planets without being stopped. The neutrinos arrived about 7 hours before the light, not because they traveled faster than light, but because they escaped the collapsing star more easily. Light was trapped in the outer layers of the star, scattered and absorbed and re-emitted countless times before finally breaking free, while neutrinos streamed out almost immediately. When scientists compared the arrival times carefully, accounting for all the known physics, they found that both the neutrinos and the light must have traveled at very nearly the speed of light, consistent with expectations within the measurement errors. It was a beautiful confirmation that even in the extreme environment of a supernova, the speed of light remains what theory predicts. And if we look back even further, to the earliest moments of the universe, we encounter a puzzle that the speed of light helped to solve. The cosmic microwave background is a faint glow of radiation that fills all of space, the cooled remnant of the hot plasma that filled the universe when it was only 380,000 years old. This radiation is remarkably uniform in all directions, varying in temperature by only about 1 part in 100,000. But here is the puzzle. If we look at opposite sides of the sky, we are seeing regions of the early universe that were so far apart that light would not have had time to travel between them since the Big Bang. They were beyond each other's horizons, causally disconnected, unable to influence each other. So how did they end up at almost exactly the same temperature? The answer, most cosmologists believe, is a process called cosmic inflation, a brief period in the universe's first fraction of a second when space itself expanded far faster than the speed of light, not violating relativity because nothing was moving through space faster than light, but rather space itself was growing exponentially. This inflation stretched a tiny region of the early universe, a region small enough that light could have smoothed out its temperature, into a vast expanse much larger than the observable universe today. The uniformity we see in the cosmic microwave background is the legacy of that inflationary epoch, a time when the universe expanded faster than light could cross it, solving a problem that the finite speed of light had created. When we look out into the night sky, we are looking back in time, seeing light that has been traveling toward us for years, for centuries, for millions or billions of years depending on how far away its source lies. The universe is old, about 13.8 billion years according to our best measurements, and you might think that means the farthest thing we could possibly see would be 13.8 billion light-years away, that distance being how far light could have traveled in the age of the universe. But the observable universe is actually much larger than that, extending to a radius of about 46.5 billion light-years in all directions. This seems like a contradiction, like a violation of the principle that nothing can travel faster than light, but it is not. The expansion of the universe is not objects moving through space, but space itself growing, carrying galaxies along with it. This metric expansion, as it is called, means that the distance between us and distant galaxies has been increasing over time, and a galaxy whose light has taken 13.8 billion years to reach us has been carried away by expansion during that time, so that it is now much farther away than 13.8 billion light-years. The space between us and that galaxy has been stretching the whole time the light was traveling, and so the observable universe is larger, much larger, than a simple calculation based on light travel time would suggest. This expansion has another strange consequence. There are galaxies so far away that they are receding from us faster than the speed of light, not because they are moving through space at that speed, but because the space between us and them is expanding fast enough that the distance grows at a rate exceeding light speed. This does not violate relativity because the galaxies are not moving through space faster than light. Rather, space itself is expanding, and relativity places no limit on how fast space can grow. There is a boundary called the Hubble sphere, roughly 14 billion light-years away, beyond which galaxies recede from us faster than light. We can still see some galaxies beyond this boundary because they emitted their light when they were closer, before expansion had carried them so far away, but we will never see light from galaxies that are currently beyond a certain distance, because the space between us and them is expanding so fast that the light will never catch up, never close the gap, even though it travels toward us at the maximum possible speed. This idea of space itself expanding faster than light has inspired physicists to wonder whether something similar could be used for travel, whether space could be manipulated in a way that would allow a spacecraft to reach distant destinations faster than light without actually moving through space faster than light. In 1994, a physicist named Miguel Alcubierre proposed a solution to Einstein's equations of general relativity that describes a kind of warp drive, a bubble of warped spacetime that contracts space in front of a spacecraft and expands space behind it, effectively carrying the spacecraft along at speeds that could be faster than light from the perspective of a distant observer. Inside the bubble, spacetime would be flat, and the spacecraft would not be moving faster than light relative to the space immediately around it, so it would not violate relativity locally. This is a beautiful idea, mathematically consistent with general relativity, but it comes with enormous problems. It would require exotic matter with negative energy density, something that has never been observed and may not exist. It would require amounts of energy comparable to the mass energy of entire stars. And even if it could be built, there are questions about whether it could be controlled, whether anything inside the bubble could influence its motion, whether causality would be preserved or violated. The Alcubierre drive remains a fascinating theoretical construct, a proof that the equations of relativity allow for strange possibilities, but it is not a blueprint for a real technology, not something we have any prospect of building in the foreseeable future. Throughout our exploration of the speed of light, we have encountered the idea that nothing with mass can reach or exceed it. But what if there were particles that naturally traveled faster than light, particles that could never slow down to light speed just as ordinary particles can never speed up to it? Such hypothetical particles are called tachyons, and they appear in some theoretical frameworks, allowed by the mathematics of relativity if you are willing to accept certain strange properties. Tachyons would have imaginary mass, in the mathematical sense of involving the square root of -1, and they would require less energy to go faster, opposite to ordinary particles which require more energy as they accelerate. Tachyons would also violate causality in disturbing ways, potentially allowing signals to be sent backward in time. Despite decades of searches, no tachyon has ever been detected, and most physicists believe they do not exist. If they did, they would render the universe unstable, creating paradoxes and contradictions that seem incompatible with the consistent reality we observe. The speed of light remains the barrier, the limit that divides the possible from the impossible. Even black holes, those regions of space-time where gravity is so strong that nothing can escape, are not entirely permanent. Stephen Hawking showed in the 1970s that black holes slowly emit radiation, a quantum effect that occurs at the event horizon. In the quantum vacuum, pairs of virtual particles constantly appear and disappear, borrowing energy from the vacuum for brief instants before annihilating each other. Near the event horizon of a black hole, one particle from a pair can fall into the black hole while the other escapes, and the escaping particle becomes real, carrying energy away from the black hole. This Hawking radiation, as it is called, causes black holes to lose mass over time, to evaporate slowly, extremely slowly for large black holes, taking far longer than the current age of the universe, but faster for smaller ones. The radiation travels at the speed of light, as all electromagnetic radiation does, carrying information and energy away from the black hole, though in a form so scrambled that it may be impossible to reconstruct what fell in, a problem known as the black hole information paradox. Virtual particles also play a role in the forces we experience every day. The electromagnetic force, the force between charged particles, is mediated by virtual photons, photons that appear briefly, transmit the force, and disappear, all in a time so short that they do not violate the conservation of energy because of the uncertainty principle. These virtual photons do not travel faster than light. They cannot be used to send information faster than light. They obey the same speed limit as real photons, preserving causality, ensuring that cause always precedes effect, that the universe remains consistent and understandable. There is another quantum phenomenon that seems, at first glance, to allow faster-than-light communication, though it does not. Quantum entanglement links pairs of particles in such a way that measuring one instantly affects the other, no matter how far apart they are. If you have two entangled particles and you measure the spin of one, the spin of the other becomes determined instantly, even if it is on the other side of the galaxy. This has been confirmed in countless experiments and is a genuine feature of quantum mechanics, not a mistake or a misunderstanding. But here is the crucial point. You cannot use this effect to send information. The results of measurements on entangled particles are random from the perspective of either observer, and only when the two observers come together and compare their results, traveling through space at speed slower than light or sending messages at light speed, do they see the correlations. There is something called the no communication theorem, a rigorous mathematical result showing that entanglement cannot be used for faster-than-light signaling. The universe, once again, preserves its own consistency, allowing quantum mechanics and relativity to coexist without contradiction. There are other theoretical effects, predicted by quantum field theory, that seem to allow light to travel slightly faster than the speed of light in vacuum, but in practice, these effects are so small as to be undetectable. The Stjernhorst effect, for instance, suggests that in a perfect vacuum between two conducting plates held extremely close together, the quantum vacuum is altered in a way that allows photons to travel at a speed very slightly exceeding the normal speed of light in vacuum, by about 1 part in 10 to the 36th power. This is not a violation of relativity because it is a property of the particular state of the quantum fields in that region, not a change in the fundamental structure of spacetime. But the effect is so tiny, and the experimental conditions required are so extreme and difficult to achieve, that it has never been tested and likely never will be. It remains a curiosity, a footnote in the vast theory of quantum electrodynamics. There is also something called the Hartmann effect, observed in quantum tunneling experiments. When particles tunnel through barriers, passing through regions where classical physics says they should not be able to go, the time they spend tunneling seems to be independent of the thickness of the barrier. This can lead to situations where particles appear to cross thick barriers in the same time it would take them to cross thin barriers, which seems to imply speeds faster than light. But once again, closer examination shows that no information is being transmitted faster than light. The tunneling process is inherently quantum mechanical, involving probabilities and wave functions, and the apparent superluminal speeds do not correspond to anything that could be used to send a signal. The leading edge of any pulse, the part that carries the information that a signal has been sent, always arrives at or slower than the speed of light. There is one more subtlety about the speed of light that is worth mentioning, a deep issue that few people outside of physics ever encounter. We have talked about the speed of light as though it is a single well-defined quantity, but in fact, what we measure directly is the round-trip speed of light, the time it takes for light to travel from one point to another and back again. The one-way speed of light, the speed from point A to point B without returning, cannot be measured without already knowing how to synchronize clocks at the two locations. And to synchronize clocks, you need to send signals between them, which means you need to know the speed of light. It is a circular problem, and there is no way to break out of the circle without making an assumption. By convention, physicists assume that the one-way speed of light is the same in all directions, that light takes the same time to travel from A to B as from B to A, and this assumption is built into how we define time and synchronize clocks. The round-trip average must equal the standard value of the speed of light, the value fixed by definition since 1983, but the one-way speed could, in principle, be different in different directions as long as the average works out correctly. There is no evidence for such a difference, and it would require rethinking much of physics, but it is a reminder that even something as fundamental as the speed of light rests on conventions and assumptions, on choices we have made about how to describe reality. There is an experiment that reveals something subtle about the speed of light and rotation, something that shows how motion affects the way light travels in ways that might seem to violate the principle that light speed is the same for all observers. The Sagnac effect, discovered more than a century ago, uses a device called an interferometer, a tool that splits a beam of light into two paths that travel in opposite directions around a closed loop before being recombined. If the entire apparatus is rotating, the beam traveling in the direction of rotation takes slightly longer to complete its journey than the beam traveling against the rotation, and this difference in travel time creates a shift in the interference pattern where the beams meet again. This happens because, from the perspective of the rotating apparatus, the destination point is moving, either approaching or receding, and so the light has farther or less far to travel depending on which direction it goes. The effect does not violate relativity because the rotating frame is not an inertial frame, not a frame moving at constant velocity, but rather an accelerating frame, and the speed of light being constant applies only in inertial frames. The Sagnac effect is used in extremely sensitive gyroscopes, devices that can detect rotation by measuring the interference pattern of light, and these gyroscopes are accurate enough to sense the rotation of the Earth itself, that slow spin that takes a full day to complete one revolution. Some physicists have wondered whether the speed of light might not be as constant as we assume, whether it might have been different in the early universe, varying with time or conditions. These variable speed of light theories, as they are called, propose that in the first moments after the Big Bang, light traveled much faster than it does now, fast enough to allow distant regions of the universe to come into thermal equilibrium before expansion carried them beyond each other's horizons. This could solve the horizon and flatness problems, the puzzles about why the universe is so uniform and so geometrically flat, without needing to invoke cosmic inflation. These theories are speculative, and most cosmologists prefer inflation as an explanation because it is better developed and makes more testable predictions, but the idea that fundamental constants might vary is not absurd. Some models of physics beyond the Standard Model suggest that constants we think of as fixed might actually be slowly changing over cosmic time, and astronomers have looked for evidence of such changes by studying light from distant quasars, searching for tiny shifts in spectral lines that would indicate the fine structure constant or the speed of light was different billions of years ago. So far, no convincing evidence of such variation has been found, and the speed of light appears to be truly constant across all of cosmic history. We have already mentioned that gravitational waves travel at the speed of light, confirmed by observations from LIGO and other detectors to within 1 part in 10 to the 15th power. This bears repeating because it is such a powerful confirmation of general relativity. If gravitational waves traveled at any other speed, even slightly different from light speed, it would indicate that our understanding of gravity is incomplete or wrong. The fact that they travel at exactly the speed of light, as far as we can measure, tells us that gravity and electromagnetism, despite being very different forces, are both deeply connected to the geometry of spacetime, both propagate disturbances through that geometry at the same fundamental speed. The speed of light appears in the basic equations that describe how light behaves as a wave. For any wave, the speed equals the frequency multiplied by the wavelength. Frequency is how many wave peaks pass a given point per second, and wavelength is the distance between successive peaks. For light in vacuum, no matter what the frequency or wavelength, the product always equals the speed of light. Radio waves with wavelengths of meters or kilometers, visible light with wavelengths of hundreds of nanometers, gamma rays with wavelengths smaller than atoms, all travel at the same speed. The only thing that differs is their frequency and wavelength, inversely related so that their product stays constant. The speed of light is also embedded in the properties of empty space itself, in quantities that describe how space responds to electric and magnetic fields. There is something called the impedance of free space, a number that relates the strength of electric fields to magnetic fields in electromagnetic waves, and it equals the square root of the permeability of free space divided by the permittivity of free space. This works out to about 376.73 ohms, where ohms are the units of electrical resistance. This impedance governs how efficiently antennas radiate electromagnetic waves, how much of the power fed into an antenna actually gets emitted as radio waves rather than being reflected back. Every antenna engineer must account for this fundamental property of space, a property that ultimately derives from the speed of light. There is a number in physics called the fine structure constant, usually represented by the Greek letter alpha, and it has a value of approximately 1 divided by 137. This dimensionless number appears throughout quantum electrodynamics, the theory that describes how light and charged particles interact, and it determines the strength of the electromagnetic force. The definition of alpha involves the charge of an electron, Planck's constant, the permittivity of free space, and the speed of light. It is one of the fundamental constants of nature, and physicists have wondered for a century why it has the value it does. If alpha were much different, atoms would be unstable, chemistry would not work, life could not exist. The speed of light is woven into this constant, connecting the quantum world of particles to the relativistic world of space-time. When light scatters off particles, there is a characteristic length scale called the Compton wavelength, equal to Planck's constant divided by the particle's mass and the speed of light. For an electron, this wavelength is about 2.5 picometers, much smaller than an atom but still large enough to be important in quantum electrodynamics. The Compton wavelength sets the scale at which quantum effects become important for particle interactions, where the particle nature of light and the wave nature of matter both manifest clearly. Photons, the particles of light, are assumed to be massless, but what if they were not? What if they had a tiny mass, too small to have been detected yet? Theories in which photons have mass, called Proctor theories after the physicist who first studied them, predict that light of different wavelengths would travel at slightly different speeds, that electromagnetic waves would show dispersion as they traveled across cosmic distances. By observing light from distant sources and looking for evidence of such dispersion, physicists have been able to place incredibly tight limits on the photon mass, showing that if photons have any mass at all, it must be less than 10 to the negative 57 grams, an inconceivably small number. For all practical purposes, photons are massless, and light travels at exactly the speed we have been discussing. There are objects in the universe called quasars, incredibly bright sources of light powered by supermassive black holes at the centers of distant galaxies. Some quasars emit jets of matter streaming outward at speeds very close to the speed of light, and when these jets are pointed nearly toward us, an interesting geometric effect occurs. The material in the jet is moving so fast and so nearly along our line of sight that successive pulses of light emitted by the jet have less and less distance to travel to reach us. From our perspective, the material appears to be moving sideways across the sky faster than the speed of light, sometimes appearing to move at speeds of 5 or 10 times light speed. This is not a violation of relativity. Nothing is actually moving faster than light. It is an illusion created by the geometry of the situation, by the fact that the material is moving almost directly toward us, and it is called superluminal motion. Astronomers can work backward from these observations to figure out the true speed and angle of the jet, and they always find that the real motion is slower than light, as it must be. There are other ways that patterns or images can seem to move faster than light without violating any physical law. If you shine a laser pointer at the moon and sweep it quickly across the lunar surface, the spot of light can move across the moon faster than the speed of light. But the spot is not a thing, not an object. It is just where the light happens to be hitting at any given moment. Similarly, a shadow can move faster than light. If you have a large screen far away and you cast a shadow on it and move your hand, the shadow can sweep across the screen at any speed, limited only by how far away the screen is and how fast you move your hand. But shadows carry no energy, no information, no matter. They are absences of light, not things in themselves, and so they are free to move at any speed without violating the speed of light limit. These examples serve as reminders that the speed of light limits the motion of matter, energy, and information, but patterns and geometrical effects are not constrained in the same way.